Imagine an internet that cannot be hacked, a network that stretches not just across continents but across time itself, an architecture not of wires, switches, and servers, but of entanglement, a lattice of light and matter woven into a single, seamless whole. Imagine a system so precise that it could synchronize clocks across the Earth to within a heartbeat over the universe's entire lifetime. This is not fantasy. It is not science fiction. It is beginning now in laboratories that look unremarkable to the outside eye. White walls, steel tables, the quiet hum of cooling systems. And yet, within these modest chambers, the future of communication, of computing, of civilization itself is being rewritten. The name for this future is simple, almost deceptive: the quantum internet. But what it represents is anything but simple. The quantum internet is not just a faster or safer version of what we already have. It is a fundamental shift in the way information exists, a change not in degree but in kind. Today's internet is fragile. Every byte of data you send, every message, every file, every image is carried by electrons and light, encoded in bits, zeros and ones. And every bit can be intercepted, copied, corrupted. Security today is a game of mathematics, of encryption that can one day be broken. It is a fortress built of locks and codes, but every fortress has a weakness, and every code can be cracked. The quantum internet is different. It does not rely on locks, but on the laws of reality itself. At its heart lies entanglement, the strange bond between particles that Einstein once dismissed as spooky action at a distance. Entangled particles are not merely correlated, they are unified no matter the distance between them. Change one and the other responds instantly, across cities, across oceans, across worlds. When information is carried by entangled photons, it cannot be intercepted. To observe the entanglement is to destroy it. To eavesdrop is to be revealed. Security is no longer a matter of mathematics, but of physics itself. This is the promise: an unhackable internet, a global nervous system where information flows not as copies, but as quantum states, indivisible and absolute. But promises are not reality. For decades, the quantum internet has been a dream, glimpsed in fragments. 2 entangled particles here, 3 linked nodes there. Experiments more fragile than functional, more art than engineering. Entanglement is notoriously delicate, collapsing under the slightest disturbance. To build a real network, one that can span nations, requires something more. A way to generate streams of entangled photons, linked to matter, scalable, reliable. And now, that something more has arrived. In Innsbruck, Austria, a team of scientists has achieved what was once thought impossible: a scalable quantum node. Using a string of calcium ions and finely tuned lasers, they created a machine capable of generating entangled photons with a fidelity of 92%. A level of precision that no longer whispers of theory, but roars of application. Each ion qubit in their system is carefully moved into an optical cavity, where mirrors capture its photon with extraordinary efficiency. Each photon emerges entangled with its ion, forming a link between light and matter. Not 1 ion, not 2, but 10 in sequence, each producing a photon, each entangled, each a piece of a quantum register that can be scaled to hundreds. This is not a toy. This is not an illusion. This is the first architecture that could truly connect quantum devices across distances, from one laboratory to another, from one nation to another, one day, from one side of the Earth to the other. What makes this so revolutionary is not just the achievement, but its potential. Earlier experiments were like whispers of the future, fragile demonstrations that proved possibility without proving scale. The Innsbruck experiment is different. It is not proof of concept, but proof of architecture. It shows a way forward, not just linking a few particles, but building registers, building systems, building networks. And the stakes are enormous. A quantum internet would not only secure communication against any spy or hacker, It would transform computing itself. Imagine quantum computers, machines that already hint at solving problems impossible for classical systems, not as isolated devices, but as nodes in a single unified machine, entangled across continents, sharing states, multiplying power. A computer not the size of a room or a city, but of a planet. And then, time itself. The quantum internet could link optical atomic clocks so precise that they would lose less than a second over the lifetime of the cosmos. A global timekeeping system so accurate that navigation, science, and civilization itself would be recalibrated. For the first time in history, the entire Earth could tick to a single, perfect rhythm. But every beginning hides its shadows. The same precision that can secure could also surveil. The same power that can unite could also divide. What happens when nations wield unhackable communication? When corporations own the nervous system of the world? When the very concept of privacy, of independence, dissolves in the face of entanglement? The quantum internet has begun. It is not finished, not built, not yet global. But the path is open and the steps are being taken. The question is no longer whether it can be done. It is whether we are ready for what it will mean. Because this is not just technology. It is not just science. It is the rewriting of the story of information itself. And once the story is rewritten, there is no going back. The modern internet is an empire. It stretches across the globe, invisible but omnipresent, woven into cables beneath oceans, satellites above the clouds, towers rising from every horizon. It carries voices, faces, transactions, secrets. Every email, every bank transfer, every confession whispered into a phone is reduced to streams of bits, zeros and ones racing through fiber and air. It feels unshakable, it feels permanent, but it is not. The empire of the internet is fragile. Every bit, no matter how hidden, can be copied. Every lock, no matter how strong, can be broken. Encryption, the armor of our age, is only as strong as the mathematics behind it. Today's codes may take centuries to crack with classical computers, but quantum computers, once matured, could break them in hours. The fortress is strong today, but tomorrow it may crumble with a single breakthrough. Already the cracks show. Data breaches expose millions of identities. Cyber attacks cripple pipelines, hospitals, cities. Governments spy, corporations harvest, black markets thrive. We live inside an architecture of surveillance, one that no firewall can ever fully seal. Every transaction is a potential weakness, every password a potential breach. This is the fragile present, a world built on trust in mathematics that can be undone by mathematics. A world where security is temporary, where privacy is conditional, where the empire of bits is only as safe as the slow pace of technological change. And that pace is accelerating. Quantum computers are still young, fragile themselves, but the day is coming when their power will not only simulate molecules and optimize logistics, but also tear open the locks of today's internet. RSA, AES, elliptic curve, the codes we trust, will fall. When they do, the foundations of communication, banking, governance, even the military will quake. We are standing at a cliff's edge. The internet that has bound civilization for half a century is approaching obsolescence. What lies beyond it is uncertain, but it is here, at this precipice, that the quantum internet emerges, not as luxury, but as necessity. Because the quantum internet does not rely on trust in codes, it relies on the laws of physics. At the heart of this lies entanglement. When two particles are entangled, their states are unified no matter the distance. Measure one, and the other responds instantly. This is not correlation in the classical sense. It is unity at the level of reality. To intercept an entangled state is to destroy it. To spy is to reveal oneself. The very act of observation collapses the entanglement. This is the key. A quantum network does not need locks that can be broken, because any intrusion is instantly visible. Security is no longer conditional. It is absolute. But security is only the beginning. For just as the classical internet reshaped civilization, the quantum internet promises transformations we cannot yet measure. Distributed quantum computing could link machines across the globe into a single vast computer. Problems too large for one processor could be divided among many, each entangled with the others, their states unified across oceans. It would not be the sum of many computers, but one computer spread across continents. Quantum sensing could measure time and environment with impossible precision. Clocks entangled across the globe would tick in unison, losing less than a second over the universe's entire lifetime. Navigation could achieve accuracy beyond GPS, immune to interference. The very fabric of measurement would be rewoven. Communication itself would change. Not just faster, not just safer, but different in kind. Quantum teleportation, the transfer of states without transfer of matter, could one day move information in ways that defy today's categories. And yet, for all these promises, the quantum internet remains fragile in its infancy. Entanglement is delicate, collapsing under heat, noise, vibration. Early experiments linked 2 or 3 qubits at most, producing photons with limited fidelity. The dream was clear, but the path seemed blocked by fragility. This is why the Innsbruck experiment matters. By creating a scalable quantum node, one that entangles ions and photons with 92% fidelity, they showed a way to move from fragility to architecture. Not just isolated demonstrations, but a design that can grow. For the first time, the quantum internet is not only necessary, but possible. But before we step further into its promise, we must fully face the fragility of the world we leave behind. Because only then can we understand why the leap is not luxury, but survival. Consider how civilization has always been bound to communication. Writing enabled empires, the printing press enabled revolutions, the telegraph enabled nations, the internet enabled globalization. Each new medium reshaped power, culture, humanity itself. Now communication is under threat, not because it will stop, but because it will fail to protect. An internet that can be broken is not an internet that can endure, and in the shadow of quantum computing, the internet as we know it is already broken. This is the crisis of the present, and it is in crisis that new architectures are born. The Innsbruck experiment is not merely an achievement of physics, it is a turning point in history, the moment the fragile present gave way to the possible future. But what is that future? What does it look like to build not a network of machines, but a network of reality itself?
That is the question we face.
And to answer it, we must go back. Back to the first fragile attempts to entangle light and matter, to the small steps that led to this leap. Because only by seeing where we began can we understand how far we have come and how far we have yet to go. Every revolution begins with fragile steps. The dream of a quantum internet, vast and unbreakable, was not born whole. It began as whispers in physics journals, fleeting flashes of possibility in cramped laboratories. Before Innsbruck, before scalable nodes, there were fragile entanglements, fragile links, fragile hopes. The problem was always the same. Light and matter belong to different worlds. Light, carried by photons, is swift, elusive, intangible. Matter, whether atoms or ions, is heavy, local, stubbornly fixed in place. To build a network, you need both. Photons to carry information across distance, matter to store it in memory. The challenge was not creating one or the other, but binding the two into a single quantum state. This is where the first experiments faltered and triumphed in equal measure. At the dawn of the 21st century, physicists began to entangle single atoms with photons. These experiments were delicate dances. A single atom trapped in an optical cavity, coaxed by lasers to emit a photon whose polarization matched its own quantum state. If successful, the atom and the photon were entangled. Two players in a duet, one fixed, one free. The fidelity was low, The efficiency was lower. Many photons were lost, their entanglement imperfect. Noise interfered, vibrations spoiled the results, heat scattered the fragile links. But the principle was proven. Light and matter could be bound. The first whispers of a quantum network had been heard. From there, the experiments grew. Pairs of ions trapped in electromagnetic fields were entangled and then connected to photons. Researchers in the United States, Europe, and Asia built isolated setups, each demonstrating fragments of the dream. A few entangled photons here, a memory stored in an atom there. Nothing yet scalable, nothing yet stable, but each experiment pushed the boundary. In 2004, a milestone, entanglement distribution across kilometers of optical fiber. Photons, fragile as they are, managed to carry quantum states over practical distances. The losses were immense, but the principle held. If photons could be entangled across kilometers, then one day they could span continents. Still, the question remained, how to connect them reliably to matter? How to build a system where photons were not just carriers, but partners, entangled with atomic qubits, feeding into quantum memories that could store, process, and retransmit. The years that followed saw a cascade of ingenuity. Different laboratories tried different approaches. Some used neutral atoms, others trapped ions, others superconducting circuits. Each had strengths, each had weaknesses. Neutral atoms were abundant but harder to control. Ions were precise but cumbersome. Superconducting circuits worked well on chips but struggled with photons. What united them all was fragility. Early entanglements were like cobwebs, beautiful, delicate, and easily broken. A vibration in the lab, a fluctuation in the laser, a stray photon of heat, all could collapse the entanglement. Scaling up was not just difficult, it seemed impossible. And yet, the experiments continued. One breakthrough came with cavity quantum electrodynamics, the use of mirrors to trap photons in tiny spaces, forcing them to interact with atoms. The cavity amplified the chance of entanglement, like a stage amplifying the voice of a singer. With each reflection, the photon's probability of coupling to the atom increased. Efficiencies rose, fidelity improved. Another breakthrough came with better trapping of ions. Using electric fields, physicists could line up strings of ions, each a potential qubit, cooled to near absolute zero to minimize motion. These ion strings became the prototypes of quantum registers, primitive processors waiting to be connected. Still, the connection to light was weak. Entangling 1 or 2 ions with photons was possible, but scaling to 3, 4, or 10 seemed out of reach. By the 2010s, experiments had shown atom-photon entanglement, but only in limited cases. Laboratories in Maryland, Boulder, Paris, and Beijing reported successes, each adding a piece to the puzzle. Some managed to link 2 nodes in the same building. Others pushed photons into optical fibers for longer distances. But the networks were brittle, the entanglement fleeting. The world of physics held its breath. Was the quantum internet only a dream, a mathematical possibility, forever just beyond engineering? Then came the incremental but relentless march of progress. Single-ion systems gave way to 2-ion systems. 2-ion systems gave way to 4. Each step demanded not only technical mastery, but philosophical patience. The willingness to coax the universe into revealing its secrets, one fragile experiment at a time. By the early 2020s, researchers had begun to link small registers of ions with photons, creating prototypes of nodes. But these nodes were modest, 2 or 3 ions at most, each entangled with a photon. Demonstrations of principle, but not yet technology. And yet, within these fragile beginnings, the future was seeded. Because every experiment, every imperfect entanglement proved a point. Light and matter can be linked. The duet can be played. The challenge was no longer whether it could be done, but how to do it well, how to do it reliably, how to do it at scale. This is the path that led to Innsbruck. A path paved not in breakthroughs alone, but in failures, in incremental gains, in fragile cobwebs that collapsed again and again. For each collapse revealed something new, a way to strengthen the trap, to refine the laser, to polish the mirrors. Slowly the cobwebs became threads, the threads became strands, and the strands hinted at a rope strong enough to bind light and matter into networks. Looking back, it is easy to see the narrative, the small experiments leading to larger ones, the fragile links building to robust architectures. But in the moment, it was never so clear. In the moment, it was doubt and persistence. In the moment, it was scientists staring at screens in the dim glow of laboratories, wondering if the numbers would hold, if the entanglement would last. This is the forgotten truth of revolutions. They are not sudden. They are not born in blinding flashes. They are grown in patience, nurtured in fragility, carried by people willing to endure failure after failure until the breakthrough comes. And the breakthrough did come. In Innsbruck, Austria. A string of ions, a set of mirrors, a carefully tuned laser. Out of that fragility emerged something new. A node, scalable, robust, precise. 10 ions, 10 photons, each entangled, each a seed of a network that could one day span the globe. The dream that once seemed fragile had taken root. The cobwebs had become architecture. And with that architecture, the quantum internet stepped from speculation into history. The laboratory in Innsbruck is quiet. White walls, stainless steel benches, racks of electronics humming in monotone. To the untrained eye, it looks ordinary, even dull. A tangle of wires, mirrors and consoles. But in this room, reality itself was bent into a new shape. Here, the fragile dream of the quantum internet crossed a threshold, transforming from possibility into architecture. The experiment was deceptively simple in description, impossibly complex in execution. At its heart were calcium ions, charged atoms stripped of electrons, suspended in electromagnetic traps. These ions were not loose, not drifting. They were arranged in a string, a register of qubits waiting to be manipulated. The choice of calcium was no accident. Calcium ions are among the most studied systems in quantum computing. They can be trapped, cooled, and controlled with exquisite precision. Each ion can serve as a qubit, storing quantum information in its internal energy levels, and crucially, calcium ions can be coaxed to emit photons when excited by lasers, photons whose polarization carries the fingerprint of the ion's state. The challenge is capturing these photons. Left alone, most escape unnoticed, flying off into the void. To build a network, that could never be enough. You need to collect them with ruthless efficiency, channel them, and preserve their entanglement with the ions. The Innsbruck team solved this with optical cavities, tiny chambers bounded by mirrors polished to near perfection. When an ion was moved into one of these cavities, the mirrors bounced its emitted photon back and forth, amplifying its chance of being captured. Instead of scattering into the void, the photon emerged directed, usable, entangled. One by one, the ions were shuttled into the cavity, like dancers moving across a stage, each stepping into the spotlight, each emitting its photon before moving aside. The process was meticulous, precise, repeatable. For each ion, a photon. For each photon, entanglement. The result, a stream of light tied to matter, a chain of ion-photon pairs woven into a quantum register. The numbers tell the story. Fidelity, the measure of how perfectly the photon was entangled with its ion, reached 92%. This was not perfection, but it was astonishing. In quantum experiments, every percentage point matters. Fidelity in the 70s or 80s signals proof of principle. Fidelity above 90 signals technology. It means the process is not just possible, but reliable. Earlier experiments had managed entanglement between one ion and one photon, or perhaps two or three. But they were static, limited, fragile. The Innsbruck experiment shattered that ceiling. 10 ions, 10 photons, each pair entangled with remarkable fidelity. And the system was not capped at 10. The architecture is scalable, in principle to hundreds. This is not just an experiment. It is a blueprint. Blueprints matter. They turn curiosity into civilization. The first transistor was a curiosity. The first laser was a curiosity. But once their architectures were refined, they became the foundations of a world. The Innsbruck experiment is such a moment. To appreciate why, consider the flow of the process. Each ion in the register can be individually addressed by electric fields. Each can be shuttled into the cavity. Each can be pulsed with a laser, producing a photon whose polarization is entangled with the ion's quantum state. The photon is captured by the mirrors, channeled and directed outward. And then the ion returns to the register, its memory preserved, its entanglement intact. Repeat the process for each ion, and you produce a stream of photons, each tied to a different ion. These photons are the messengers. They can travel down optical fibers, across laboratories, across cities. If two such photon streams meet at a distant node, their entanglement can be swapped, linking the ions in separate registers. This is the essence of a network, not isolated nodes, but nodes entangled across distance, unified into a single system. The Innsbruck experiment did not yet perform the distant linking, but it laid the foundation. It demonstrated that a single register could produce a stream of entangled messengers with fidelity high enough to support large-scale networking. It showed not just possibility, but scalability. This is why the scientific community took notice. For years, the quantum internet had been more metaphor than roadmap, more aspiration than engineering. Innsbruck changed that. It showed a path to scale, the one word that matters most in the transition from physics to technology. But numbers and architecture alone do not capture the significance. What happened in that lab was a weaving of worlds. Light and matter, once separate domains, were bound together in a system that could grow beyond the room, beyond the city, beyond the Earth itself. The photons that emerged carried not just light, but information tied to matter. They were bridges, slender but real, between the immovable and the intangible. And with bridges come consequences, because bridges invite us to cross. Entanglement fidelity of 92% is not the end. It is the beginning of engineering improvements, refinements, iterations. Each percentage point gained opens new possibilities. Each extension of the register broadens the scope of the network. What Innsbruck demonstrated was not just that light and matter can be linked. That had been known. They demonstrated that it can be done with enough precision, enough scalability, that the dream of a quantum internet has stepped out of speculation. This is why Ben Lanyon, the lead scientist, emphasized scalability. Linking 2 or 3 qubits was never enough. That was proof of principle. To connect computers across continents, you need registers of hundreds, thousands. And now, the principle scales. The breakthrough was not flashy, no glowing machines, no dazzling displays. It was quiet, technical, incremental, and yet seismic. Because revolutions often arrive this way, not with thunder, but with the hum of lasers and the silence of trapped ions. In the history of communication, Innsbruck will be remembered not for spectacle, but for architecture. The first node that could grow, the first design that could scale, and from here the path is open, toward networks of quantum devices, linked by streams of photons, toward an internet where security is physics, not code, toward clocks so precise they can measure the heartbeat of the universe. The Innsbruck breakthrough is not the end of the story. It is the first chapter of a new one. And the next chapter asks, how does it work? What is the machinery of entanglement fidelity, of ion registers and photon streams? How do we move from 10 to 100, from 100 to 1,000? Because if Innsbruck showed us that it can be done, the next step is understanding how. In the language of headlines, the Innsbruck breakthrough sounds simple, Scientists created a scalable quantum node linking light and matter. But behind that simplicity lies a machine as intricate as a cathedral, a structure built not of stone and glass but of ions, lasers and mirrors. To understand it, imagine a stage. At the center are the dancers, calcium ions, suspended in an electromagnetic trap. Each ion is a qubit, capable of holding quantum information in its delicate energy states. The trap holds them in a line, a string of dancers awaiting their cue. But these dancers are restless. Left alone, they vibrate, they scatter. To be useful, they must be calmed. And so they are cooled to near absolute zero, stripped of their thermal motion until they hover almost motionless, like beads of light frozen in air. Only then can they be choreographed with precision. The choreography comes from lasers, beams of light tuned with unimaginable accuracy. Each pulse of a laser is like the conductor's baton, commanding the ions to move, to change state, to emit. The laser does not simply illuminate, it instructs. It tells the ion when to release a photon, what polarization that photon should carry, and how it should remain entangled with the ion's own quantum state. This is the essence of the process. The ion and the photon bound in entanglement, one anchored, one free. But if the photon escapes into the void, the duet is lost. And so the Innsbruck team built a chamber to hold it, the optical cavity. The cavity is a hall of mirrors, but not ordinary mirrors. These are polished to near perfection, reflecting photons thousands of times before letting them escape. When an ion sits inside, any photon it emits is trapped, bouncing back and forth until it aligns with the cavity's mode. When it finally leaves, it does so not as a scattered emission, but as a directed beam, a clean messenger ready for the network. Now imagine the dance in motion. The electric fields shift. The first ion glides into the cavity. A laser pulse strikes, and the ion releases its photon. The mirrors capture it, refine it, and then release it outward, entangled with the ion left behind. The ion is then moved back into the register, and the next ion takes its place. Again the pulse, again the photon, again the entanglement. One by one, the dancers step forward, perform their duet with light, and return. The result is a stream of photons, each entangled with a different ion in the register. A chain of messengers, each carrying the quantum fingerprint of matter. This is the essence of the Innsbruck node. A mechanism that binds light and matter, not once but repeatedly, scalably, reliably. But the magic lies not only in the choreography but in the precision. The lasers must be tuned to extraordinary accuracy. The electric fields must guide ions without disturbing their quantum states. The mirrors must reflect without scattering. Every element must operate in harmony, or the entanglement collapses. It is a triumph not only of physics, but of engineering. And the numbers prove it. The entanglement fidelity, the degree to which the photon and ion states matched, reached 92%. In everyday terms, this means that in nearly every case, the photon carried exactly the information encoded in its ion partner. Noisy experiments might achieve 50%, good ones 70 or 80, but 92% is architecture. It is high enough that error correction becomes possible, high enough that scaling is realistic, high enough that the dream of a quantum network takes form. What does this fidelity mean in practice? It means that if two such nodes were placed in distant labs and their photons guided into optical fibers, the entanglement could be swapped. Photons from one node could meet photons from another, their interference linking the ions behind them. In this way, distant registers could be connected, not by cables or signals, but by entanglement itself. The Innsbruck team did not yet build the global network, but they built the machinery that makes it possible. For the first time, a register of 10 ions produced a stream of entangled photons, each one a potential bridge to another node. For the first time, light and matter were bound not in fragile pairs, but in scalable chains. This is why the experiment matters. Because in the world of quantum technology, scale is everything. Entangling 2 particles is an achievement. Entangling 10 is a revolution. Because 10 can become 100, and 100 can become 1,000, and 1,000 is enough to build a network that spans the Earth. But behind the numbers, behind the engineering, lies something deeper. What the Innsbruck team created is a machine that binds the immovable and the intangible. Matter, heavy and local, becomes linked to light, swift and global. The photon carries the ion state outward, across space, across possibility. It is as if the walls of the laboratory dissolve and the quantum state of matter extends into the world, woven into the fabric of light itself. This is more than technology. It is metaphor made real. Matter and light, once separate domains, now entangled. The anchored and the free, the fixed and the fleeting, bound into one. And with this binding, the future opens. Because once light and matter can be reliably entangled, the building blocks of the quantum internet fall into place. Nodes can be constructed, linked, scaled. Networks can grow. The promise of unhackable communication, distributed computing and global clocks begins to move from theory to reality. But to appreciate the weight of this breakthrough, we must look more closely at what those photons carry, because each photon is more than a particle of light. It is a fragment of information, a messenger of possibility. It is entanglement made visible, and to understand that, we must turn to fidelity, to the meaning of 92% and why that number changes everything. In physics, numbers are everything. They are the line between illusion and reality, between spectacle and substance. For the quantum internet, one number stands above all: fidelity. Fidelity measures truth. It tells us how faithfully a quantum system does what it claims. When an ion is entangled with a photon, fidelity measures the overlap between the ideal state, perfect entanglement, and the actual state produced. A fidelity of 100% is impossible perfection, a dream of theory. A fidelity of 50% is noise, barely distinguishable from randomness. So when Innsbruck announced an average fidelity of 92%, the number carried weight beyond mathematics. It carried the weight of trust. To grasp why, we must understand what low fidelity means. In a low-fidelity system, errors accumulate. Entanglement collapses under the strain of noise, stray vibrations, or imperfect measurements. One error may seem small, but networks amplify errors. In a chain of entangled particles, each link must hold. If one link falters, the chain breaks. At scale, low fidelity is fatal. Earlier experiments hovered in the 60s, 70s, sometimes into the low 80s. Impressive, yes, but fragile. The errors compounded too quickly. The dream of scaling up to networks of tens or hundreds of qubits evaporated in the noise. But 92% is different. At this level, errors shrink to the point where quantum error correction becomes viable. Instead of collapsing, networks can endure. Instead of compounding, mistakes can be identified and mitigated. 92% is not perfection, but it is enough to cross the line from demonstration to design. Think of it like aviation. The first aircraft could fly, but barely. They wobbled, they crashed, they were curiosities. But once engineering reached the threshold of reliability, flight became not just possible, but practical. 92% fidelity is that threshold for the quantum internet. It is not flawless flight, but it is flight stable enough to build an airline. How is this fidelity achieved? Precision at every stage. The ions were cooled to near absolute zero to minimize thermal noise. The optical cavity was engineered to trap and refine each photon, ensuring it emerged clean and directed. The lasers were tuned with astonishing accuracy, their pulses calibrated to imprint the ion's quantum state onto the photon. Every mirror, every lens, every field was optimized to reduce error. Even then, achieving 92% was not trivial. It required iteration, calibration, endurance. Hours of adjustment to coax each component into harmony. Fidelity is not a gift. It is earned through relentless refinement. But fidelity is more than a technical detail. It is a philosophical threshold. Because fidelity tells us whether we are glimpsing reality or chasing illusion. When fidelity is low, skeptics can dismiss the results as artifacts. Perhaps the entanglement was only partial. Perhaps the measurement was noisy. Perhaps the system did not do what it claimed. At low fidelity, doubt is reasonable. At 92%, doubt evaporates. The numbers speak too clearly. The system entangled ions and photons, and it did so with precision. The dream is not fantasy. It is measurable, it is repeatable, it is real, and fidelity has consequences. At 92%, you can imagine networks where nodes exchange entangled photons without collapsing. You can imagine linking multiple registers across laboratories, across cities. You can imagine error-corrected architectures that persist, scale, endure. This is why Innsbruck's number matters. It is not just higher than before. It is high enough to change the category of what is possible. Consider again the chain of photons emitted from the register. Each photon, entangled with its ion, is a messenger. If their entanglement is weak, the message is garbled. If it is strong, the message is clear. At 92%, the messages are clear enough to be trusted. Trusted to travel down fibers, trusted to link nodes, trusted to support a network. In this way, fidelity is the foundation of the quantum internet's promise. Without it, networks collapse. With it, networks emerge. And yet 92% is not the end. It is a beginning. Future refinements may push fidelity higher, closer to 95, 98, perhaps even 99%. Each step will open new possibilities, making networks more robust, more scalable, more useful. But already, 92% is enough to declare a milestone, enough to silence doubt, enough to shift the dream from theory to engineering. The Innsbruck breakthrough is not just about ions, photons, and cavities. It is about fidelity, the measure of truth. And in truth, the quantum internet has begun. But fidelity alone is not the whole story. It tells us that the architecture works, but it does not tell us how it will grow. The next question is scale. How do you move from 10 ions to 100, from 100 to 1,000, from a laboratory to the world? That question is not philosophical, it is practical, and it is the question we must face next. Every revolution begins in confinement. The steam engine began in a mine. The transistor began in a laboratory basement. The internet itself began in the sterile offices of ARPANET, linking a handful of machines across a handful of universities. What began confined eventually spread, transforming the world. The Innsbruck quantum node is no different. Today it exists in a single room. Mirrors, lasers, and calcium ions suspended in traps, producing streams of entangled photons, fragile, controlled, overseen by physicists in lab coats. But the destiny of this machine is not confinement. Its destiny is to grow, to escape the lab and to become a network. The path from lab to network is not obvious. It requires both vision and engineering. But the blueprint is there, etched into the process Innsbruck demonstrated. Step 1 is duplication. A single quantum node, however perfect, cannot form a network. You need at least 2, ideally many more. Each node is a register of ions, each ion a qubit capable of entanglement with photons. By duplicating the architecture, building nodes in different laboratories, you create the potential for connection. Step 2 is transmission. The photons emitted from each node must travel. Optical fibers are the natural medium. They already span the world, carrying classical information at the speed of light. But quantum information is different. Photons carrying quantum states cannot be amplified the way classical signals can. They must survive the journey intact, without copying, without interruption. Losses are inevitable. The challenge is to minimize them. Here is where Innsbruck's high fidelity matters. If photons are born with 92% fidelity, they have a fighting chance of surviving kilometers of fiber with useful entanglement intact. Earlier experiments with fidelity in the 60s or 70s stood little chance. Their photons were too fragile, their messages too garbled. But 92% can endure, can travel, can connect. Step 3 is entanglement swapping. Imagine two nodes, each emitting photons into the world. If two photons from different nodes meet at a central station and interfere, their entanglement can be swapped. The photons vanish, but their entanglement is transferred backward, binding the ions that emitted them. In this way, two distant registers become linked, not by direct contact, but by shared entanglement across light. This is the key mechanism of a quantum network. Photons carry the entanglement outward, swapping links the nodes, and the nodes, once linked, can share quantum information directly. Step 4 is repetition. One link is fragile, but many links, chained together, form a network. Nodes entangled across cities, across nations, across continents, each link reinforcing the next, building resilience, building scale. Step 5 is architecture. Just as the classical internet required protocols, TCP/IP, packet switching, routing, the quantum internet will require its own architecture. Protocols for entanglement distribution, protocols for error correction, protocols for synchronizing quantum states across distance. These are not yet written, but they are being drafted in theory, and Innsbruck's node provides the hardware to test them. Step 6 is application. Once networks exist, once entanglement can be distributed, the uses multiply. Secure communication, distributed computation, global timekeeping. Each application will push the network further, demanding more nodes, higher fidelity, longer distances. The applications will not wait for perfection. They will grow as the network grows, step by step, iteration by iteration. This is the path from lab to network. It is not quick and it is not easy, but it is real, and it has been walked before. Think of the early internet. In 1969, ARPANET linked 4 computers. The connections were fragile, the protocols clumsy. Few could imagine the global web of today, with billions of devices, trillions of connections. The quantum internet today is ARPANET in 1969, fragile, modest, confined, but the path is open and the growth is inevitable. The difference is that the stakes are even higher. Because the quantum internet does not merely promise faster communication, it promises unbreakable communication. It promises computing power that no classical system can match. It promises clocks so precise that civilization itself can be synchronized beyond imagination. From lab to network is not a matter of convenience, it is a matter of necessity. The fragile present of classical communication is crumbling. Encryption will fall, trust will collapse. Only a quantum internet can endure. But to move from lab to network requires more than engineering. It requires will. It requires nations, corporations and institutions to see the stakes, to invest, to build. Already efforts are underway. China has launched satellites carrying entangled photons. The United States, Europe and Japan are funding quantum communication projects. Innsbruck's node is not alone. It is part of a rising tide. Still, there is fragility. The photons are delicate. The distances are vast. The costs are immense. But revolutions are always fragile at the beginning. What matters is not that the network is strong today, but that it can grow stronger tomorrow. And Innsbruck has shown that growth is possible. 10 ions, 10 photons, 92% fidelity. From this seed, forests can grow. But the leap from lab to network raises deeper questions. Because when light and matter are bound into networks, when entanglement stretches across nations, what does it mean for information itself? What does it mean for knowledge, for power, for humanity's place in a world where reality itself becomes the medium of communication? The quantum internet is not just a technical project, it is a philosophical one. It challenges our understanding of distance, of security, of time. It invites us to imagine a world where information is not copied but shared as one. From lab to network, from ion to photon, from Innsbruck to the world, the path is open. The only question is how far we will walk it. The world we live in today is built on bits. Every message, every film, every heartbeat recorded on a monitor is reduced to the same language, zeros and ones. Classical information is binary, discrete, solid. It is the language of computers, of networks, of the internet that binds our civilization. But bits are not the whole story. They are an approximation, a simplification, a shadow of something deeper. Beneath the surface of the digital world lies another language, stranger, richer, and infinitely more fragile. This is the language of quantum information. The difference is not subtle. It is not merely a matter of speed. It is a matter of ontology, of what information is. A classical bit can be a 0 or a 1, nothing more. It is like a light switch, off or on. Billions of bits strung together create images, sounds, words. But each bit is blunt, absolute. There is no ambiguity, no superposition. A quantum bit, a qubit, is different. It can be 0 or 1 or both at once, not metaphorically, but physically. In quantum mechanics, a system can exist in superposition, occupying multiple states simultaneously until measured. The qubit does not choose until forced. It holds possibility itself. This is the first rupture between classical and quantum information, certainty versus possibility. Classical information is definite. Quantum information is probabilistic, fluid, alive. The second rupture is entanglement. Classical bits are independent. One bit knows nothing of another unless connected by a program. But quantum bits can be entangled, bound together in a unity so deep that they cease to be separate. Change one and the other responds instantly, no matter the distance. They are not two systems, but one system stretched across space. This is what Einstein called spooky action at a distance. But in the quantum internet, it is not spooky, it is architecture. Entanglement means information is no longer local. It is not stored here or there. It is shared. It is everywhere the entangled partners exist. Classical networks transmit copies. Quantum networks transmit states. The distinction is not small. It is the difference between sending a photograph and sharing an experience. The third rupture is fragility. Classical bits are resilient. A file can be copied, backed up, duplicated endlessly. A quantum state cannot. The no-cloning theorem forbids it. Quantum information cannot be perfectly copied. It can only be transmitted, shared, entangled. This makes it powerful, but also delicate. The very act of observing collapses it. Security becomes absolute, but stability becomes the challenge. To build a network of classical information is to build an empire of copies. To build a network of quantum information is to build a web of entanglement. The classical internet is an archive. The quantum internet is a mirror of reality itself. This is why Innsbruck's achievement matters so deeply. By entangling ions with photons at scale, they built a machine that bridges these two worlds. The ions store quantum information, the photons carry it outward. Together they form a node, a meeting place between matter and light, between local memory and global transmission. Think of the metaphor. Classical information is like ink on paper. Permanent, copyable, archival. Quantum information is like breath on glass, fleeting, unique, impossible to replicate. To build the quantum internet is to learn to capture the breath without losing it, to pass it from glass to glass without shattering. The contrast is almost philosophical. Classical information feels safe, predictable. Quantum information feels alien, uncanny. Yet our world is already shifting toward the alien. Quantum computers, even in their infancy, hint at powers classical machines cannot match. They can factor numbers that secure our banks. They can simulate molecules that determine life itself. They can optimize problems so complex that classical algorithms fail. But computers are only as powerful as their connections. One isolated machine is a marvel. A network of machines is civilization. The classical internet taught us this. The quantum internet will teach us again. And yet, this difference cuts both ways. Because quantum information is fragile, the network that carries it must be careful. There are no repeaters, no amplifiers, no copies. Every photon is unique, every state unrepeatable. When it is lost forever. This is why Innsbruck's fidelity matters. Because in the fragile world of quantum information, 92% fidelity is not just a number. It is a lifeline. It is enough to trust that the message will survive the journey. But even as the architecture emerges, we must pause to consider what this difference means for us. The classical internet reshaped humanity. It created globalization, social media, surveillance, misinformation, democracy movements, collapses, revolutions. It changed how we love, how we fight, how we think, all from networks of zeros and ones. What will the quantum internet do? Built not of zeros and ones, but of possibility, entanglement and fragility. What will it mean to live in a world where communication itself is no longer a matter of copies, but of unity? Will it mean security as promised, an end to hacking, an end to espionage? Or will it mean something stranger, a civilization where knowledge is no longer exchanged but shared, where distance no longer separates but binds? Quantum information is not just a new technology, it is a new way of thinking, a new way of being. And Innsbruck's node is the first step into that world. But to truly grasp its power, we must follow it into the future. Because quantum information does not just secure communication, it transforms computing itself. It creates the possibility of distributed quantum machines linked across continents, united into a single intelligence. And that future is closer than we think. Picture an internet where every message is absolute. No leak, no eavesdropper, no spy can pierce it. Imagine sending a signal across oceans, across nations, across orbit, and knowing with certainty that only the intended recipient can read it. Not because of locks, not because of passwords, but because the very laws of physics make intrusion impossible. This is the promise of the quantum internet. A network not of secrecy but of inevitability, where security is not an option but a consequence of reality itself. In the classical internet, trust is fragile. Encryption is a puzzle, and every puzzle can be solved. Given enough power, every lock can be broken, every message revealed. The security of today's world is temporary, a truce between the strength of mathematics and the weakness of machines. Tomorrow's machines, quantum computers themselves, will shatter that truce. The quantum internet rewrites the rules. Its messages are not puzzles to be solved, but entangled states. To observe them without permission is to collapse them, to expose the spy. The act of intrusion is the act of self-destruction. This is not security by design, it is security by physics. Governments dream of it, militaries crave it, corporations plot to own it. A network that cannot be hacked is not just an advantage, it is power itself. But the quantum internet promises more than secrecy. It promises unity. Imagine quantum computers in Tokyo, London, New York, and Sydney, all linked into a single machine by streams of entangled photons. Distance becomes irrelevant. Processing power becomes shared. Problems too large for one machine dissolve when many act as one. The internet becomes not a web of separate nodes, but a single entity stretched across continents. The implications are staggering. Drug discovery accelerated, climate models perfected, financial systems optimized beyond human comprehension, weapons systems calculated with unimaginable precision. Every strength carries its shadow. And then, time itself. Optical atomic clocks already tick with precision that defies imagination. Linked through entanglement, they could form a global heartbeat, synchronizing civilization with accuracy so great that it would lose less than a second over the entire lifetime of the universe. Navigation would be transformed, science would be recalibrated, Time, the most intimate of illusions, would be unified across the earth. But in this vision of the future, we must also see the shadows. A network that cannot be hacked is also a network that cannot be escaped. Who controls such a system? Who decides who may access it, who may connect, who may be excluded? When information itself becomes entanglement, privacy is no longer a question of encryption, but of participation. To be outside the quantum internet may mean to be outside civilization itself. The future internet will not merely be faster, it will not merely be safer, it will be different in kind. It will be a nervous system, binding the world not with wires but with physics. It will be a mirror, reflecting the unity of quantum states across distance. It will be a cathedral of entanglement, fragile and absolute, delicate and unbreakable, and it will not be optional. Just as the classical internet crept into every corner of life, from commerce to romance, from war to governance, so too will the quantum internet. At first, it will be confined to governments, laboratories, corporations, but in time it will descend into daily life, woven into phones, watches, homes, invisible, inevitable. The question is not whether this will happen. The question is how we will live in its shadow. Will it bring a golden age of communication, knowledge, and unity, or will it fracture the world into those who control the entanglement and those who do not? Will it liberate, or will it enslave? The quantum internet is a mirror. In it, we may see the best of ourselves, cooperation, precision, discovery, or the worst, domination, surveillance, exclusion. The technology itself is neutral. It is we who will decide its destiny. But destiny has a way of escaping choice. Once a technology exists, it spreads. Once a path is open, it is walked. The Innsbruck node is a door, and behind it lies a world we cannot yet imagine. The future internet will not only connect devices, it will connect reality itself. And in that connection, in that web of entanglement, humanity will be changed. The only question is, into what? The internet we know today began as a way to connect machines. Alone, a computer was powerful. Connected, computers became civilization. Each device fed into the network and the network fed back, multiplying capacity, multiplying reach. The true power of the internet was never in the single machine. It was in the many. The same truth waits at the threshold of the quantum internet. A quantum computer on its own is extraordinary. Even in its infancy, it can solve problems classical computers cannot touch. It can simulate molecules for new medicines, optimize logistics for global trade, probe equations that describe the universe. But a single quantum computer, no matter how advanced, is still limited. Its qubits are finite. Its coherence is fragile. Now imagine linking them. Imagine a lattice of quantum computers spread across continents, each entangled with the others. Together they cease to be separate machines. They become one machine, distributed, unified, planetary in scale. This is distributed quantum computing, and it is the destiny of the quantum internet. How would it work? At its core, the principle is simple. Each quantum computer is a register of qubits, capable of storing and manipulating quantum information. By entangling qubits across distant machines, you fuse their registers. Suddenly, what was two machines becomes one larger machine. A processor in Europe, linked to a processor in Asia, now acts as if it were one, its qubits shared across oceans. The Innsbruck breakthrough makes this imaginable, a node that can entangle ions with photons, photons that can travel, photons that can link distant nodes. One by one, the links can be forged. 10 ions become 10 bridges. 10 bridges connect 10 machines. Scale that, and you no longer have computers separated by geography. You have a single computer spread across the world. The implications are staggering. Drug discovery, already accelerated by quantum simulation, could become instantaneous. Climate models, with their billions of variables, could be solved with precision beyond today's supercomputers. Cryptography, finance, artificial intelligence, All could be transformed by the sheer magnitude of distributed quantum power.
But it is not only science and commerce that would change. Distributed quantum computing carries a philosophical weight because it challenges the very idea of separateness.
In the classical world, networks connect by transmitting information. One machine sends data to another. They remain distinct even as they communicate. In the quantum world, entanglement unifies. Two machines do not merely exchange, they become one. Their qubits are not separate but shared. Their states are not local but global. This is not communication, it is communion. And communion changes everything. Imagine artificial intelligences not running on separate machines, but entangled across continents. Imagine their cognition not as isolated processes, but as a planetary mind, distributed yet singular. The internet has already blurred the boundaries of individuality. The quantum internet could erase them altogether. Of course, the road is long. The challenges are immense. Quantum systems are fragile. Entanglement is delicate. Photons are lost. Coherence collapses. Errors accumulate. But the principle is clear. The architecture exists. And history has shown that what can be built in principle will be built in practice. Distributed quantum computing would not simply be powerful, it would be irreversible. Once machines are entangled across continents, the world will change in ways we cannot fully predict. Nations will race to build it, corporations will fight to own it, scientists will struggle to harness it. But the outcome will be the same: a global intelligence, woven of light and matter, operating at scales beyond imagination. And yet, as with all revolutions, the shadows grow alongside the light. Who controls such a machine? Who decides which problems it solves, which questions it answers? What happens when the combined intelligence of the planet is not guided by humanity, but by power, by profit, by war? The classical internet gave us connection but also division. It gave us knowledge but also misinformation. It gave us unity but also surveillance. The quantum internet will be no different. Its distributed computing power will amplify the best and the worst of us. But unlike the classical internet, the quantum internet will not be optional. Once it exists, it will dominate. Its power will dwarf classical machines. Its networks will outpace classical communication. To ignore it will be to step outside civilization itself. Distributed quantum computing is not just a dream of efficiency. It is a transformation of being, a redefinition of intelligence, a challenge to individuality itself. Picture a future where every scientific discovery is accelerated, every model perfected, every calculation instantaneous. Picture also a future where control over that machine becomes the most valuable commodity on Earth, the power to cure or to kill, to create or to destroy, to liberate or to enslave, all held in the entangled hands of a network too vast to comprehend. This is the destiny of the quantum internet. Not simply unhackable communication, not simply global clocks, but distributed intelligence at planetary scale. And when it arrives, humanity will face a choice, though perhaps not a choice at all. To resist is to fall behind. To accept is to be changed. The future of computing is not local. It is not even global. It is entangled. And in that entanglement, the line between machine and world will blur. The question is not whether distributed quantum computing will come. The question is whether we are ready for the civilization it will create. Time is the most intimate measure we possess. It governs our days, our memories, our lives. Empires have risen and fallen by the keeping of time. Farmers once read the heavens to plant their crops. Sailors measured the stars to cross oceans. Railroads, telegraphs, and empires demanded synchronized clocks to keep their networks aligned. Civilization itself has always been a story of mastering time. But our clocks are not perfect. No pendulum swings forever without friction. No quartz crystal vibrates without drift. Even the best atomic clocks lose track eventually, slipping a fraction of a second over millions of years. To us, this is perfection. To the universe, it is still error. The quantum internet promises to erase even this imperfection. Optical atomic clocks, already the most precise instruments ever built, measure time by the oscillations of electrons in atoms ticking trillions of times per second. Their precision is staggering. If one had begun counting at the dawn of the universe, it would have lost less than a second today. And yet, linked through quantum networks, even this precision can be surpassed. Innsbruck's entangled nodes are not just communication tools, they are timekeepers. By linking clocks across the world through streams of entangled photons, humanity could synchronize every instrument, every device, every heartbeat of civilization to a single rhythm. Imagine a planet ticking as one. Laboratories in Tokyo, satellites in orbit, observatories in Chile, submarines beneath the Arctic ice, all locked to the same universal time, precise to within a fraction of a second. The implications are profound. Navigation would be revolutionized. Today's GPS relies on atomic clocks in satellites, drifting just enough to cause errors of meters. A global quantum clock would make positioning exact to millimeters. Aircraft could land themselves. Ships could dock with precision beyond eyesight. Autonomous vehicles could navigate without error. Science, too, would be transformed. Astronomers could align telescopes across continents into a single virtual dish, their observations fused without lag. Gravitational waves could be detected with sharper clarity. Dark matter, elusive and hidden, might reveal itself in tiny fluctuations of universal time.
Even more staggering, the global clock could test the very fabric of physics. General relativity predicts that time flows differently depending on gravity. Clocks on mountaintops tick faster than clocks at sea level. With a network of entangled clocks, humanity could measure these differences with unprecedented precision, mapping the subtle warping of space-time itself. But the deepest implication lies in philosophy. A global clock would mean for the first time that humanity shares a single heartbeat. Today, time is local. My second may not be your second. My clock may drift from yours. But in a world of entangled time, there would be only 1 second, 1 beat, 1 measure of existence.
This is more than technology, it is identity. Imagine what it would mean to live in such a world. Wars fought on split-second decisions, stock markets operating at speeds measured in trillionths, science probing mysteries once thought eternal. A civilization unified not by borders or beliefs, but by time itself. And yet, as always, shadows accompany light. A global quantum clock could be a tool of control. Who owns the heartbeat of civilization? Who decides how it is distributed? Who may connect? Who may remain outside? In the wrong hands, time itself could become a weapon. Nations could control access. Corporations could monetize precision. The rhythm of reality could become property. Even without malice, dangers remain. Precision can amplify fragility. Systems that rely on perfection can collapse catastrophically when perfection falters. A single disruption in the global clock could ripple across navigation, communication, finance, warfare. When all of civilization ticks as one, the failure of the clock becomes the failure of the world. Still, the dream is irresistible. A clock that loses less than a second over the lifetime of the universe. A network that binds not only communication but existence itself. The Innsbruck experiment is a step toward this dream. 10 ions, 10 photons, 92% fidelity. A seed of a network that could one day span the earth. From such seeds grow forests. From such experiments grow civilizations. Time has always been the measure of our progress. Sundials gave way to pendulums. Pendulums gave way to quartz. Quartz gave way to atomic clocks. And now atomic clocks give way to entangled networks. Each step more precise, each step more binding, each step drawing humanity closer to unity. The quantum internet is not only a nervous system for the world, it is a heartbeat that could outlast the stars themselves. But precision raises deeper questions. If time can be measured so perfectly, then what is time? Is it a rhythm of atoms, a tick of electrons, a consequence of entropy? Or is it something deeper, something woven into the fabric of reality itself? And if one day we can control time's flow across the Earth, will we be content to measure it, or will we try to master it? The global quantum clock is not just a promise of accuracy, it is a doorway to mystery. And mystery, as always, is where science meets philosophy. Every technology carries two shadows, what it promises and what it threatens. Fire warms, but it burns. The printing press spreads knowledge, but also propaganda. The internet connects, but also surveils. The quantum internet will be no different. For every dream it brings, it carries a nightmare. We must ask, what happens when the most powerful network in history, unhackable, precise, planetary in scale, is used not to liberate, but to control? The first danger is ownership. The quantum internet will not arrive as a gift to humanity. It will be built, funded, and controlled by nations, corporations, and alliances. Its infrastructure will be expensive, its technology complex. Those who control it will wield the most valuable commodity of the future, not oil, not data, but entanglement itself. An unhackable network sounds like liberation. But what if it is owned by the few? A government that controls entangled communication controls the flow of truth. A corporation that owns the backbone of the network owns not just information, but time. A world where access to the quantum internet is restricted would be a world divided, the entangled and the excluded, the precise and the obsolete. The second danger is surveillance. Ironically, the same physics that promises security could also enable total control. Entangled communication is unbreakable by outsiders. But what if you are the insider? What if the state or corporation that provides access also observes the endpoints, not the entanglement itself, but the devices that use it? A world where communication is unhackable may also be a world where communication is unescapable. The third danger is weaponization. Distributed quantum computing, linked across continents, could solve problems classical supercomputers cannot even attempt. Some of those problems are benign: drug discovery, climate modeling, financial optimization. Others are not: weapons design, cryptography cracking, strategic simulations of war. An entangled network could accelerate not just science, but destruction. And then there is time. A global quantum clock sounds like unity, but in warfare, timing is everything. Precision beyond imagination could give militaries an edge so vast it erases competition. Missiles could be synchronized to nanoseconds. Drones could act in perfect unison. Cyber warfare could unfold faster than human comprehension. Whoever owns the global clock could dominate the tempo of war itself. The fourth danger is fragility. Quantum networks are precise, but precision breeds vulnerability. A single disruption, a severed fiber, a misaligned node, a compromised satellite could ripple across the entire system. The tighter the synchronization, the more catastrophic the failure. Civilization ticking as one heartbeat is elegant, but also perilous. When the heart falters, the body collapses. The fifth danger is philosophical. Entanglement erases separateness. In distributed computing, machines cease to be independent. In global clocks, time ceases to be local. What happens to individuality in such a world? When distance no longer separates, when information is not exchanged but shared, what does it mean to be distinct? The quantum internet may not only transform technology, it may transform identity. And yet, the greatest danger may be inevitability. Once the architecture exists, it will be built. Nations will race to deploy it, corporations will rush to profit from it, militaries will weaponize it. Even if the risks are known, the rewards are too great. Like nuclear weapons once discovered, entanglement cannot be undiscovered. Once built, the quantum internet cannot be uninvented. This is the paradox of progress. The very qualities that make the quantum internet extraordinary, unbreakable security, distributed intelligence, precision beyond imagination, are the same qualities that make it terrifying. We must also remember, technology never evolves in isolation. The quantum internet will not arrive into a neutral world. It will arrive into a world of competition, of inequality, of surveillance states and corporate monopolies. In such a world, what are the odds that it is used purely for liberation? The Innsbruck experiment showed us what is possible: 10 ions, 10 photons, 92% fidelity, but it also showed us what is coming: a network that will redefine communication, computation, and time, a network that may liberate or enslave. The dangers are real, but they are not reasons to halt progress. They are reasons to confront it, to ask before the architecture spreads how it should be governed, who should own it, who should be trusted to wield it. The quantum internet will not wait for philosophy, but philosophy must not wait for it. Still, one truth remains. Danger is the shadow of possibility. The brighter the promise, the darker the shadow. And the quantum internet burns bright indeed. The Innsbruck node is a doorway. Beyond it lies a world transformed, but also a world imperiled. The dangers are not reasons to turn back. They are reminders that progress always asks the same question: not can we, but should we? And if we should, then under what terms? Because if we fail to ask, the terms will be written by power. And history has shown again and again that power rarely writes with mercy. At its core, the quantum internet is not just wires and photons, nodes and registers. It is not even just security, computation, or clocks. It is something deeper, a transformation of what connection means. For most of human history, connection has been metaphor. We speak of hearts connected, of minds aligned, of societies bound together by invisible threads. But these were figures of speech. In reality, we remained separate. Our words traveled across distance, our messages crossed oceans, but our being remained divided. The quantum internet changes that. Entanglement is not metaphor, it is reality. Two particles once entangled are no longer two. They are one system, stretched across space. The distance between them is irrelevant. They are unified, indivisible, absolute. What does it mean then to build a network on this foundation? Classical networks connect by exchange. A message leaves me, travels to you, and arrives altered, copied, stored. The communication is external. In quantum networks, the connection is internal. The states are shared. The entanglement is not exchanged, but experienced together. The separation dissolves. This challenges not only technology, but philosophy. For centuries, we have built our worldview on separateness. I am here. You are there. My time is mine. Your time is yours. Nations are distinct, identities unique. Even communication assumes distinction. Sender and receiver, signal and noise. But the quantum internet whispers another story. A story in which separateness is illusion, in which distance is irrelevant, in which unity is not dream, but fact. When two photons are entangled, they are not two, but one. When two nodes are linked, they are not communicating, but sharing. When time is synchronized across the globe, it is no longer local, but universal. This is not just physics, it is metaphysics. Consider identity. If my qubit is entangled with yours, what does that mean for individuality? If my state depends on yours, if our information is shared at the deepest level, am I still only me? Or are we, in some sense, a larger unity? The quantum internet suggests that individuality is not absolute, but relational. Consider knowledge. In classical terms, knowledge is transmitted. I tell you something, and now you know it. In quantum terms, knowledge may be shared. Our systems overlap. Our states intertwine. The act of connection is itself an act of knowing. To be entangled is to be informed. Consider time. We are accustomed to local clocks, to private seconds. But in a world of entangled clocks, there is only one time, one measure of existence. Time ceases to be subjective, ceases to be mine or yours. It becomes a shared rhythm, a universal beat. This raises questions as old as philosophy itself. If separateness is illusion, what is reality? If individuality dissolves in entanglement, what is the self? If time itself can be shared, what is eternity? For centuries, mystics have spoken of oneness, of unity beyond distance, of the interconnectedness of all things. Physics now offers a mechanism for such unity, not mystical but measurable, not dream but experiment. The quantum internet is not a metaphor for oneness, it is oneness made operational. And yet, we must be cautious. Entanglement does not erase causality. It does not allow faster-than-light messages or communication with the past. It does not make mysticism true, but it does make connection stranger than our philosophies imagined. It suggests that reality itself is relational, that the boundaries we take for granted, self and other here and there, now and then, are not absolute. They are approximations, useful but incomplete. The Innsbruck node, then, is not only a technological breakthrough, it is a philosophical one. It shows us that communication can be built not on exchange, but on unity, that networks can be woven not of copies but of shared states, that time itself can be measured not locally but universally. This forces us to ask, what kind of civilization emerges from such a foundation? The classical internet created a world of copies, files duplicated, messages archived, information replicated endlessly. We became a civilization of storage, of surplus, of memory. The quantum internet creates a world of presence. No copies, no archives, only shared states that collapse when observed. A civilization of immediacy, of fragility, of truth that exists only in the moment of entanglement. Is such a civilization possible? Or will we resist it, clinging to the comfort of separateness, of permanence, of control? Perhaps the answer lies not in resistance, but in transformation. Just as the printing press reshaped thought, just as the internet reshaped identity, the quantum internet will reshape philosophy. It will force us to rethink self, time, and connection. It will not ask permission. It will not wait. And in that reshaping lies both terror and beauty. Terror because it dissolves the boundaries we cling to. Beauty because it reveals the unity we have always suspected. The Innsbruck experiment is a doorway. Beyond it lies not only a new internet, but a new philosophy of being. A philosophy where connection is not metaphor, but fact. Where unity is not dream, but architecture. Where the deepest truths of physics and the oldest questions of philosophy meet. What does it mean to live in such a world? We do not yet know, but the question is no longer hypothetical. The photons have been entangled, the fidelity has been measured, the door is open, and once open, doors are seldom closed. The quantum internet is often imagined as terrestrial, fibers laid under oceans, satellites orbiting above, nodes humming in laboratories. But entanglement is not bound by geography. It does not care for borders, oceans, or even planets. If the principle holds across a meter, it holds across 1,000,000 kilometers. Distance does not weaken entanglement. It only makes it harder to preserve. What then does it mean to build not a planetary network, but a cosmic one? The first step is already happening. In 2017, China's Michus satellite demonstrated quantum communication between ground stations separated by thousands of kilometers. Entangled photons were generated in orbit, then sent down to Earth, linking cities on opposite sides of the planet. It was fragile, it was early, but it proved the point. Entanglement can be distributed not only across laboratories, but across the heavens. Now imagine scaling this further. A web of satellites blanketing the Earth, each node generating and distributing entangled photons. A global shell of entanglement, binding the planet in a skin of light. This is the immediate cosmic scale. Earth itself wrapped in a nervous system that reaches not only under oceans, but above clouds. But the vision does not stop at Earth. Humanity is a spacefaring species, however tentatively. Probes leave the solar system. Rovers crawl across Martian soil. telescopes orbit the Earth and gaze at galaxies billions of light years away. Each of these machines is isolated, dependent on slow, fragile radio waves. Signals from Mars take minutes to arrive. Signals from Pluto take hours. Signals from stars take years. Distance dilates communication. Entanglement offers another path. In principle, an entangled photon generated on Earth could be paired with its twin, carried to Mars. No matter the distance, their states remain linked. When measured, they correlate instantly. This does not violate relativity. No information travels faster than light. But it does allow networks of entangled states to stretch across worlds, creating correlations no classical signal could match. Imagine a Martian colony linked to Earth not only by radio waves, but by entangled nodes. Their clocks synchronized to fractions of a second across millions of kilometers. Their quantum computers entangled with ours, sharing states across planets. Humanity would no longer be bound by the delay of distance. We would live in shared presence, even as we spread into space. Extend this vision further. Probes sent to the outer planets, each carrying entangled nodes. Telescopes on the Moon, entangled with observatories on Earth, fusing their data instantly into a single aperture the size of 2 worlds. Spacecraft venturing beyond the solar system, carrying half of an entangled pair, forever linked to its twin on Earth. Could such entanglement survive the vastness of interstellar space? In theory, yes. Entanglement does not degrade with distance. In practice, maintaining coherence across such scales is almost unimaginably difficult. Photons scatter, particles interact, noise creeps in, but every barrier is technical, not fundamental, and technical barriers have a way of falling. If they do, the consequences are staggering. Imagine a cosmic quantum network spanning planets, moons, stations, ships. Humanity spread across the solar system, yet ticking to one clock, computing as one mind, secured by one unbreakable web of entanglement. The philosophical implications deepen. Distance has always been one of our most profound realities. The stars are beautiful precisely because they are unreachable. Even within our solar system, communication delay reminds us of scale. Mars is far not only in kilometers, but in minutes. The stars are far not only in light years, but in years of waiting. But what if distance ceases to matter? What if our networks are no longer slowed by kilometers, but unified by entanglement? What does it mean when presence extends beyond the Earth, when humanity lives in a single informational state across space? Perhaps it means that civilization itself will shift, no longer earthbound but solar system-wide, yet as unified as a single planet. Entanglement could make humanity multiplanetary not only in biology, but in consciousness. Mars and Earth could share computation, share time, share security, as seamlessly as 2 cities share data today. And beyond the practical, there lies a haunting question. Could entanglement extend not only across space, but across civilizations? If intelligent life exists elsewhere, could their networks ever entangle with ours? Could entanglement be a cosmic language, a universal architecture of connection, transcending light years? We do not know. Perhaps entanglement is too fragile. Perhaps coherence cannot survive the void. Or perhaps someday we will discover that across the stars, someone else has been weaving the same web. For now, the cosmic quantum internet is a dream. But it is a dream seeded in reality. Mikius has proven photons can be entangled across Earth. Innsbruck has proven ions can entangle scalably with light. Between these steps lies the possibility of scale beyond our planet, and scale, once possible, is inevitable. The quantum internet may begin in laboratories, but it will not end there. Its destiny is cosmic. Its architecture is universal. Its implications stretch not only across continents, but across worlds. One day, humanity may look up at the night sky not as a void, but as a network of light and matter woven across planets, moons, and stars, a nervous system not of Earth, but of the cosmos. The quantum internet begins in Innsbruck, but its horizon is infinite. Civilization is not built on stone or steel, it is built on communication. The first cities rose when people could record grain tallies on clay tablets. Empires expanded when they mastered long-distance messengers. Revolutions erupted when printing presses spread dangerous ideas. The telegraph, the telephone, the internet, each new medium reshaped the structure of power, economy, and identity. The quantum internet will be no different. But its effects may be deeper, stranger, and more irreversible than any that came before. Consider nations. Today, borders are reinforced by control of information, firewalls, surveillance, censorship, encryption. States compete to protect their communications while undermining those of their rivals. But what happens when communication becomes unhackable, when entanglement makes interception impossible? The balance of power shifts. Espionage, once the currency of states, withers. Transparency emerges not from choice but from physics. At the same time, nations will compete to own the architecture. Whoever builds the first planetary quantum network may control the backbone of civilization. Just as railroads once defined empires, entangled nodes could define the future. A country with mastery over entanglement might secure not only its own networks, but deny them to others. Borders might harden, not soften, as access to the quantum internet becomes the prize of geopolitical struggle. Now consider corporations. Today, the tech giants own the internet's infrastructure, servers, clouds, cables, satellites. Tomorrow, they may own the quantum nodes, the entangled registers, the networks of light and matter. What is the value of advertising when a company could own the heartbeat of civilization itself? What is the value of social networks when you could own the network of reality?
Monopoly in this arena would be absolute. A corporation that controls entangled communication, distributed quantum computing, and global clocks would not merely dominate markets. It would define civilization. Governments would orbit its power, individuals would live within its architecture. The corporation would not sell a service, it would sell reality.
Economics too would transform. The quantum internet collapses distance. Computation becomes global, instantaneous. Timekeeping becomes universal. Finance, already measured in nanoseconds, would accelerate beyond human comprehension. Markets would not just fluctuate, they would evolve in entangled rhythms. Traders would no longer compete on speed, they would compete on access to entanglement, access to precision. Wealth itself could become quantum. And beneath these shifts lies culture. Communication is culture. The internet created a world of immediacy, of constant presence, of information without borders. The quantum internet would deepen this. If entanglement collapses distance, what becomes of place? If time is synchronized globally, what becomes of tradition, of calendars, of local rhythms? A civilization unified by entanglement may discover that diversity itself is strained. One beat, one network, one architecture. But perhaps the deepest change is psychological. We are accustomed to separateness. We define ourselves by borders, by difference, by distance. What happens when distance collapses, when separateness dissolves, when communication becomes unity rather than exchange? The quantum internet may not only reshape politics and economics, it may reshape identity. At the edge of civilization, one question looms. Who are we when we are all entangled? The answer may not be gentle. The internet of today has given us connection, but also isolation. It has amplified voices, but also silenced them. It has liberated, but also enslaved. The quantum internet will magnify these contradictions. Its promise of security may become control. Its promise of unity may become conformity. Its promise of precision may become fragility. And yet we cannot step back. History does not retreat. Once the architecture exists, it will spread. Nations will race to deploy it. Corporations will profit from it. Individuals will adapt to it. Civilization itself will reorganize around it. We stand, as we have stood many times, at the edge of transformation. When the printing press spread across Europe, few imagined it would topple empires. When the telegraph clicked across oceans, few imagined it would create global markets. When the internet crept into dorm rooms, few imagined it would define existence. Today, as Innsbruck's photons entangle with ions, few imagine the civilization it will create. But it will create one. Perhaps a world of liberation, where communication is safe, where science thrives, where humanity unites in shared time. Perhaps a world of control, where power consolidates, where access is restricted, where individuality dissolves. Perhaps both, coexisting in tension, as all technologies do. The Innsbruck node is more than a machine. It is a seed of civilization. The civilization that grows from it is still unknown. But history has taught us one thing. The future is never what we expect. It is always stranger, always darker, always brighter, and the quantum internet, poised at the edge of civilization, will be no exception. Every story must end, though no ending is ever final. The story of the quantum internet, of light entangled with matter, of ions dancing with photons, of nodes and networks that may one day span the Earth and beyond, is only just beginning. Yet even at the start, we glimpse the contours of its conclusion. It is not about faster messages, it is not about stronger encryption, or even about clocks that outlast the stars. At its deepest level, the quantum internet is about what it means to be connected. Not metaphorically, not digitally, but physically, bound by the laws of nature themselves. When Innsbruck's team guided ions into their optical cavity and coaxed photons into entanglement, they did more than prove a principle. They created a mirror in which we see ourselves, refracted through the strangeness of quantum mechanics. We see unity where we thought there was separation. We see fragility where we thought there was strength. We see possibility where we thought there were limits. The quantum internet is a machine, yes, but it is also a philosophy made manifest. It tells us that separateness is not absolute, that distance is negotiable, that information is not something to be copied and stored, but something to be shared and dissolved. It tells us that civilization is not built of stone or steel or even silicon, but of connections, and that those connections are stranger, deeper, and more haunting than we ever imagined. And so we arrive at the final question. What does it mean to live in a world where light and matter themselves are entangled into one network? Perhaps it means liberation, a civilization where espionage ends, where privacy is preserved by physics, where science accelerates, where medicine, climate, and knowledge advance at the pace of entangled thought. A golden age, secured by the unbreakable laws of nature. Perhaps it means domination. A world where access to entanglement becomes the new frontier of inequality, where nations wield quantum networks as weapons, where corporations enclose the heartbeat of time itself within walls of profit, a civilization unified not by trust, but by control. Perhaps it means something stranger still, a shift not just in politics or technology, but in being itself. When clocks tick as one across continents, when computers fuse into a planetary mind, when photons carry the fingerprints of ions across the void, humanity may discover that individuality, distance, even identity itself, are not what we believed. Perhaps the self is not singular, perhaps the future is not local, perhaps reality is not separate. This is the haunting truth. The quantum internet is not only about what we can do, it is about who we become. The story began in Innsbruck. 10 ions, 10 photons, 92% fidelity, fragile numbers, but enough to bend the arc of history. From there, networks will grow, nodes will multiply, entanglement will spread. Satellites will beam photons across oceans. Laboratories will stitch together continents. Clocks will synchronize, computers will merge, and one day, perhaps sooner than we imagine, civilization itself will awaken as a web of light and matter. When that day comes, we will look back on the early experiments, on the mirrors, the traps, the lasers, the whispers of entanglement in the quiet Austrian lab, and we will know. This was the moment the door was opened, and beyond that door only questions remain. Will we walk through into liberation or into control? Will we build a civilization of unity or of domination? Will we wield the quantum internet as a tool, or will it wield us? The future is uncertain, the architecture is inevitable, and so we stand at the threshold of a new age. An age where communication is not exchanged but shared, where time is not measured but unified, where intelligence is not local but planetary. An age where the deepest mysteries of the universe, unity, distance, reality itself, become the foundation of our networks. The Innsbruck experiment is over. The entanglement has been measured, the fidelity recorded, the photons released. But the story of the quantum internet has only begun, and we are left with the question that haunts all progress, the question whispered at the edge of every breakthrough, the question that will echo through the centuries to come, when light and matter themselves are bound into one network, when civilization is rewoven by entanglement, when the very fabric of reality becomes our medium. What will we do with it? Thank you for joining us on this extraordinary journey through the universe here on Frontiers of Infinity. If this glimpse into the unknown has sparked your curiosity, be sure to subscribe and join us where we unravel the darkest mysteries of space.